transformation. Okay. What we're going to find out, and I think I should mention this before we get into it because it did arise in the last class, and because I have, and obviously been doing this since I was your age, I've figured this out, and I just want to make sure that you understand before you get into it, and you're saying, well, every one of these graphs that we're making looks the same. My argument to that is that no, they don't, because of what the axes are written in, okay, in terms of scaling things. So my argument is if I were to look at, let's just go back to, let me actually cancel this out, close this out and start a new one. If we go back to Algebra 1 or Algebra 2, I'm just going to graph a very simple curve here. Okay, I'm going to graph x squared. I'm going to do x squared in the green. Okay, and over here in the white, I'm going to graph something completely different. I'm going to graph 6x squared. Okay, now because the scale of the axes here is identical, right? You can tell that there's discrepancy between the curves, correct? But when I mess with the scale, wrong one. When I mess with the scale, do they look the same now? That makes sense? But they're completely different. The one on the left has a 0.11 on it. The one on the right has the 0.16 on it, right? Does that make sense to everybody? So those are things to kind of keep in mind as we're doing these curves. We might graph cosine of x, and then the next question we graph cosine of 3x, and they look the same. You know, it's because the scale has changed when we graph that cosine 3x. So, kind of see if we can model that. If I were to graph on the same scale cosine of x and cosine of 3x, obviously on the same scale, those are two different curves, right? And you can see that the 3x one is providing a compression, okay? But if I put that 3x one on the other graph, and again, I'm going to mess with the view a little bit. Standard view. Maybe it might be easier to mess with this one. Say again? Easier to make a compression something that you're also changing your axis. Yes, yes. And that's kind of actually what we're going to do here eventually. Keep doing the wrong one. There we go. All right, so we can kind of make them look somewhat the same based on adjusting the axes, right? You see that axis on the left goes 0 to 10, where on the right it's 0 to 1 is my increment, okay? And ultimately here, it actually, to me, it looks like the blue one is a more compressed function, right? Where in retrospect, the red one is actually the one that's being compressed. It's just that we've messed the scale up so bad on the blue one that it looks more compressed than the orange one. But it's the x-axis and the y-axis values that we're going to be kind of concentrating on with a lot of our pictures. Is that all right with everybody? Okay. When we deal with these functions, so let's just graph, because you guys didn't graph this one yesterday, correct? We didn't do any? All right. So I just want to kind of walk you through the general procedure for doing this. First thing you're always going to do is you're going to look at what your trig function is. Okay? and you're going to graph the parent function, ordered pairs, for that period. Okay, so if I look at this, remember the period for the cosine is 2 pi over b, where b ultimately is the coefficient of your argument. So it's the 1x right here. So that's the 1. So my period here is just 2 pi. Is that okay with everybody? Okay, so we're going to graph our parent functions on the period of 2 pi. So cosine has a ordered pair of 0, 1. It has an ordered pair of 2 pi, 1, right? The most efficient way of graphing these is to graph the starting point and then graph the ending point of one period. Then for the cosine, when you go halfway, you're going to be at -1. So halfway in that interval, we're at -1. And now what do I do halfway between each of those two intervals? Just cross the x-axis, right? So that is the set of parent function points for cosine on the interval of 0 to 2 pi. Okay? The next thing we're going to do, regardless of what transformations are present, because there's going to be multiple ones present, remember talking about this? Do anything that is horizontal first. Okay? So horizontal shifts left and right, or in this case, it's even going to be, we can think about it as horizontal horizontal stretches or compressions. Okay. The second one, you can view the S as either vertical stretches, or if you want to, at the same time, think about it as a horizontal stretches and compressions as well. Okay. So the H and the S tell you to move left and right, followed by then compressions horizontally, stretches horizontally, stretches vertically, compressions vertically. Does that make sense? Those are the first two things you got to do in that order. Okay. The next thing you want to do is do your reflections, whether they be x-axis or y-axis reflections, and then finish it off with a vertical translation. The reason we do that, if you go back to college algebra, the reason we did that in that order was that if I flip-flop the R and the V, when I do a vertical shift, the axis of reflection actually shifts with it. Does that make sense? So if my x-axis is my axis of reflection here, if I were to have a reflection, and I shift up 2 units before I do my reflection, I would actually need to reflect the x-axis. Instead of across the x-axis, I reflect across the line y equals 2 instead. And that's a messy thing to think about and keep straight. So if we can go HSRV, it automatically takes care of that, and you never run into that issue. Okay? But once we have the cosine function graph for that period, we're going to go through and say, okay, do I have horizontal shifting? And the horizontal shifting is that when I have a plus or minus something to my x, right? So we don't have that. Okay? My stretch, my vertical stretch, is determined by the amplitude. And the amplitude is that number out front, correct? Okay, of the cosine. It's that multiplier. We don't have that, so there's no vertical stretch. In regards to a horizontal compression or a horizontal stretch, we're actually going to kind of probably take care of that mostly with the period equaling 2 pi. If my period was pi, it would have been taken care of with these parent function points, and I'll talk about that when we see an example. A reflection, we're looking for a negative sign out in front of cosine or a negative sign out in front of the x, and we don't see that. Okay, so no reflection. We do, though, have a vertical shift, right? Okay, so things will be moved up 2 units. So what we do then, we take every one of these parent function points, and we add 2 to the y value. So it's a y value 1, it turn into a y value of 3, right? So y value of 0, it turn into a y value of 2, y value of -1, 1, 0 to 2, 1 up to 3. And then we use a smooth curve, as smooth as we make it, to end up creating that period. That's one cycle of the cosine function around the unit circle, right? Now, traditionally, they ask you in your homework questions or on tests and quizzes, the end of course, or the final for this course will ask you, graph this over 2 periods, or graph it between negative 2 pi and 2 pi, or graph between 0 and 4 pi. So they want you to somehow, depending on the interval they give you, indicate that you understand that based off of that period there, you should be able to take every one of these points and subtract 2 pi or add 2 pi to it to get a corresponding point in another position. Does that make sense? So if I take this point here, that point there, and subtract 2 pi from the x-coordinate, doesn't that point go right there? Take that x-coordinate and subtract 2 pi from it. That point is going to go to negative 3 pi over 2. Take this one and subtract 2 pi from it, so you go to negative pi. And keep doing that with the other points. Take 2 pi, subtract 2 pi from it, gives you 0. And now we've got 2 periods of that function graph instead of just the one. And my hopes are you realize that's just basically essentially a cut and paste procedure. Okay? Is that all right? So that's kind of one of your basic ones, just one transformation. The next one is not all that difficult either. The next one is cosine of negative x. Okay? Or not, sorry, not cosine, negative cosine of x. Negative cosine of x. So when I graph those, I'm going to, in this one, just to make things a little bit less compact, I'm going to make my top value here 1 and bottom value here negative 1. On tests and quizzes, guys, I will dictate your axes for you. I think that just makes things, in regards to me grading, a lot easier and a lot more efficient because I don't have to grade 36 different axes and how you set them up, and then it's just a pain in the butt. So, and on WebAssign, a lot of this stuff, guys. So WebAssign does not have a very good procedure for getting you to graph these. It's more of here's a function, match it up to the one that one of the 4 that we give you a picture of. And I think that's kind of counterproductive because most people are just going to graph on the A3, A4 and see what it looks like and choose that one, which is kind of silly, I think. So I will give you some worksheets in the future. So here we go. Cosine, again, parent function, 0, 1, 2 pi 1, pi, negative 1. Halfway in between, you cross the x-axis, right? So those are your 5 parent function points for cosine. And that's hopefully something, guys, that, and we've seen in the last couple of days now, it's something that is almost as natural or kind of embedded in you as asking you for 5 parent functions for x squared or 5 parent functions for y equals x. Okay, we should have those things very quickly. Now, what the negative does, negative out in front, is going to do what to each one of these y values? It's going to change them, right? It's going to change them by negative 1. It's going to flip over the x-axis. So 0, 1 is going to become 0, negative 1. What about pi or 2, comma 0? What's that going to become? Same point. And that's fine. So obviously you guys see me using different colors, right? Obviously it's a little bit, I think, more simple for me to use more colors than you guys do. But if you're graphing just the points and you're using just a black ink pen or a blue ink pen or a pencil, you got, how many points we got up there? 8? You got 8 points up there. Which ones do you connect if they're all the same color, right? My suggestion, get a highlighter, get crayons, get colored pencils. I've had people in the past get one of those fat pens that has those little clickers on it. You can change the color. And those are great for this type of thing because you can color code things, and it just makes things, I think, so much simpler. But then we're going to connect those with a smooth curve, right? Okay. It's not a rigid shape, okay? So that's one period of negative cosine x. We should then be able to mimic that, cut and paste that thing over here. And we got that thing, okay? I personally believe that in regards to getting a good smooth curve, can you watch me do these? I really struggle going from like here, like doing that, okay? When I do that, I miss so many of the points that I plotted. And then I go back and make those points just so much bigger so they do intersect. So you'll see me go from like the maximums, and I do a branch there, and go back to that and do the branch over there. And I think that allows me to get much smoother, much more consistent graph. That's something that we want to concentrate on, is making sure that it does look like a smooth curve. All right, so who plans on taking calculus at some point? Awesome. Yeah. The reason I asked that is because I want to show you. I think if you understand maybe where this stuff's going to be used, or the fact that it is going to be used again at some point, maybe it helps you currently decide that, yeah, I better learn this stuff inside out. So I'm going to take this thing here and I'm going to rotate it. It's probably going to freeze because there's a lot of stuff going on. Okay, so just you kind of see that thing down there in the bottom, right? Correct. Let me trace this thing. So trace on. What we do is, so we take the sine function and we rotate it around one of our axes, and we get that kind of shape. Does that make sense? Okay. Now, something that we're going to be interested in calculus will be, can you, by knowing that three-dimensional shape called a solid of revolution, can we determine what that shape's volume is? Can we determine that shape's surface area? Okay. If you think about that, look at that shape. Okay, does that kind of look like maybe like a piece of candy wrapped in like cellophane or something like that? Okay. Maybe I'm interested as a manufacturer that makes millions of these pieces of candy, how much cellophane I need. Does that make sense? Okay. So maybe we could do some calculus to do that math so that I can make effective and intelligent decisions about my manufacturing process. Okay. So that's kind of where this understanding of sine and cosine is going to become important to us later on in calculus. Okay. Before we get to that point, we're going to solve some equations. Okay. If I want to solve an equation, okay, and this is analogous to any other situation we've ever been in college algebra. If I have three, not just three cosine of 2x, and I want to know, I got graphics 1. And I want to know, when does that thing equal, let's go 2.5. Okay, do those things intersect? Okay, so graphically we've talked about when we solve an equation, it's looking for the x values in which two things intersect, right? Two curves intersect. So we would have the equation 3 cosine 2x equals 2.5. We should be able to algebraically go through and solve that eventually, okay? What's going to be beneficial for you is to understand how the graph operates so that you can, after you've done the analytical stuff with your, we'll use substitutions and identities and all that kind of stuff to rewrite this and make it a convenient algebraic question. It'd be nice to be able to go back graphically and prove that the answers I found algebraically do match up to the answers that are supposed to occur through the graph. Does that make sense? Okay. So graphing these things, spent a couple days on it, but my hope is that you understand kind of the purpose for learning this stuff real well, is because it's going to be a component for a lot of things that we do beyond just this section. Okay. I'm going to put this up here. It's in the PDF if you want it. PDF's on the website, I believe, under Chapter 6 somewhere. But that is 100% garbage. It's all accurate, but it's garbage. Okay? Because would you guys agree that if I asked you to memorize that stuff, that you're probably going to mess something up? Okay? You guys remember with conic sections, we messed stuff up with conic sections a lot because we had to remember so much on those. The way I tried to teach it was to help you develop relationships, right? Okay? If I learn, and this, I did the same thing when I was in Algebra 2. We learned conic sections. We learned those charts, and we learned, the equations for hyperbolas, and we learned the formulas and all that kind of stuff for foci and all that kind of garbage. And right now, I've been teaching that for 12 years. I don't know a single one of them. Okay, because they're just confusing. There's so many of them, I mess them up. But I do know the relationships on those objects that allow me that if I take 30 seconds, I can tell you what the equation of the hyperbola's asymptote is, and that's never going to leave me. Does that kind of make sense? Because of the relationships I've built with it. So the same thing's going to happen when we graph these guys. I don't want you to memorize this stuff. I think it's garbage. So in regards to learning how to do this and developing the procedure, we're going to do it through experience. Go through practice problem after practice problem to see if we can figure out a good kind of coherent process to graph these. Okay. The first thing I want to do, guys, is I think it's good to collect data, collect the information about what's going on. Okay. So the first thing that I'm going to ask is, what is the amplitude? Amplitude is always the absolute value of that multiplier out front, right? So the amplitude is 3. Okay? Now, at the same time that I write my amplitude, I'm going to make a note that there's actually a negative out front, right? What's the negative out front going to produce for us? X-axis reflection. Okay, so I'm just going to collect the information about what is taking place with this function, and then once I have all that stuff collected, then I just apply it inside the graph. Okay, I'm going to keep going through. It is the cosine function, so I know what that parent function looks like. I'm going to commit that to memory. Now I look at that. Okay, what is the b value? Remember, every one of these is a cosine b x plus c plus d. What is the B value here? B equals 1. Now, the reason I find B equals 1 is because that tells me the period. Period is 2 pi over B, which in this case is just 2 pi, right? The first couple of these that we've done, that was consistent, and what happens is people neglect it and think, well, that's true every single time. Period is not going to be 2 pi down here on this one. Okay. Are there any horizontal shifts? Phase shifts is what we usually call them. Not applicable on this one, right? Vertical shifts, not occurring, okay? So we collect that data, and eventually, guys, like on tests and quizzes, I want to know what you know. So I can't just give you one of these and say graph it and have real good understanding of what you know, right? Because you could have just, by happenstance, it happens to people, got it right because you just got lucky, okay? So what's going to happen is I'm going to ask you to graph 2 or 3 of these, and then I'm going to give you 4 or 5 equations where I ask you, list the information. Tell me what the amplitude is. Tell me if you got an x-axis reflection. Tell me if you've got a different period than 2 pi, that kind of stuff. And if you could tell me how to collect all that stuff and you can collect it correctly, then it's just a matter of putting it in a picture, and I think you could probably do that. Does that make sense? And that's an efficiency thing in terms of time on tests and quizzes. So now what we do, okay, is that we're going to go through and we're going to plot our parent function information on the period that we have developed, or the period that this function is going to exist on. So our period is that traditional 2 pi period, right? So that's kind of nice. So all we have to do is take our x-axis and find 2 pi on it. So I think I'm going to put 2 pi out here. I think mine are written. I think each one of those vertical grid lines is, I think I got a total of 12 there. Okay. So that's 2 pi. Now I'm going to cut that in half. That's what we always do. So let's start x-axis. So that's going to be pi, right? We'll cut that in half. Pi over 2. We'll cut this half. 3 pi over 2. Is that doable? Okay. Now, I'm going to plot the parent function. If this is 1, the parent function for the cosine is there. Finishes over here. Finishes at the red one. Halfway in between, it gets down here to -1. And then we've got these points as well, right? What's the 3 going to do to those? At 0.01, that 3 is going to amplify, right? So stretch it 3 units. Okay, now if I've got a negative as well for this thing, I'm not going to plot that point and say, okay, now let's flip it, right? I think we're intelligent enough that we can do that all at once. Stretch by 3, flip over the x-axis. So I'm going to do this in blue. Where's this point going to go? Nowhere. All right. Where's this one going to go? Stretch the 3, flip up here, right? Where's that one going? Nowhere. Where's this one going? Stretch 3, down there. Now, as I stretch 3 and then reflect, is that same thing as reflect and then stretch 3? So that tells you, because you got the same point, those 2 transformations are independent of one another. Does not matter the order that you do those. Totally up to you. But if I'm going off of that HSRV acronym, it's a terrible curve. Then I would stretch it first and then reflect. All right? It's 1 period of -3 cosine x. Questions on that? We're good with that one? Let's go to the bottom one there. 4 cosine 3x. Now, here's my argument. This thing might actually, Let's make that, instead of doing 4 cosine 3x, let's do negative 4 cosine 3x. Negative 4 cosine 3x. Because I want to show to you, I want to prove to you that if you do this and you make your axes kind of like the question before, in terms of size, your graphs might look almost identical here when we're done. But if we pay attention to the axes and how they're written, that should indicate that they're not different. Okay? So again, I'm going to write down what my amplitude is. What's your amplitude? 4. Okay. Do you have an x-axis reflection? Yep. Now, this number here, that's your B value, right? Okay. So your period is equal to 2 pi over B, which is 2 pi over 3. Does that make sense? Okay. Are there phase shifts or vertical shifts here? Nope. Okay. So this is ultimately the information that we need. Okay. Now, if I go out here to 2 pi over 3, okay, last question, I put 2 pi out there, right? Now it's 2 pi over 3. If you remember, and I always, when I was learning this, trying to develop a system that always worked for me, is that I always graphed the parent function on the parent function period right above the question I was doing. Okay, it doesn't have to be great, but I always went, okay, that was 2 pi. Well, right now that 2 pi and that 2 pi over 3 relate to one another. Does that make sense? Okay. And the normal parent function, that was where my period stopped. My first period stopped. This is now where my first period is stopping for this function. Does that make sense? What did we do to get another position on this x-axis? Okay, you could do that. All right. So what? Okay, let's go with that here in a minute. Up here, we cut that in half, right? That makes sense to everybody? Okay. So down here, am I going to cut that in half? So what's half of 2 pi over 3? Pi over 3. And what Derek is saying is that if this was 2 pi, and this is 2 pi over 3, come up here, because this was pi over 2, and this is 3 pi over 2. He's saying, put that over 3, put that over 3, put that over 3, put that over 3, and that will, because that's what we're really doing, that will effectively, when you convert those and reduce those pi over 2 divided by 3 stuff, it's going to give you the positions on your x-axis for 4 cosine of 3x. Does that make sense? Is that what you were saying? Yeah. Okay. So if I cut that, like I said, if I cut that one in half, then okay, that's what I like to do. But you're fine by now. I cut that in half. What's pi over 3 cut in half? Pi over 6. And now to get this one here, you can either use this idea here. Okay. So 3 pi over 6 or pi over 2. But some people prefer just to add. If that is my initial interval. That's going to repeat over and over. So that's pi over 6. It's pi over 6. Can I take pi over 6 plus pi over 6, get pi over 3? Pi over 3 plus pi over 6, give me a pi over 2. Okay, and we can keep doing that, and it'll give me the 2 pi over 3. So that's how, I think that is what people struggle with the most, is listing that x-axis and getting that done correctly. Okay, but now let's go back to the parent function. If it's a cosine, the parent function started there, finished there, right? Same thing here. Start at a height of 1, finishes at a height of 1. What was it at pi over 3? Halfway in between, it was negative 1, right? So same thing here. Halfway in between, negative 1. Those spots there are x-intercepts, right? So those are the 5 points that we're now going to transform, right? They're analogous to the 5 points that occur in a normal period 0 to 2 pi, but now they've just been squeezed down to occur between 0 and 2 pi over 3. Okay? Now, what's the 4 going to do? Stretch it. And what's the negative going to do? Reflect it. Okay? So I kind of did a crappy job of putting these points. So let's put that point there, that one there, because my axes only go up to like 3, right? So let's say that this goes by 2. So that's 2, and that's 4. So you're going to stretch it and reflect it. So it should go there. Stretch it, reflect it. Okay, so it should go. I don't know what I'm thinking. Should go there. Stretch this one, reflect it. Should go there, right? And these here on the x-axis stay the same. Now, if I graph that, does your curve, if you're somebody that kept your graphs the same size, does that curve look very similar to the one above it? Yeah. Okay. They're different. Obviously, they're different. But because of the way we structured or scaled our axes, they look similar because we're kind of more zoomed in on this, right, than what we were on the last one. I do like having the capacity of using GeoGebra to verify that they are different. And we do see, if I start with cosine x, and then I graph -4 cosine 3x, okay, you do see then when I look between, I look in this interval here, when I look inside that blue region, because that's 0 to 2 pi there, do we see that the cosine function has been compressed and then pulled vertically, right? Okay, so you do see, and it's also been reflected. You see those relationships, okay? So I do think there's benefit in being able to look at both of them at the same time on the same scale, okay? Just to give you a heads up on this, on tests and quizzes, mostly on quizzes, I'm probably going to take away your capability of using the graphing calculator, okay? I'll let you have your computers open so you can use like the Google calculator, so if you need to do multiplication or anything like that, I think everything I give you, you should be able to do in your head. But the reason for that is if I don't know how to graph -4 cosine of 3x, can I graph it on there and just go pick off points and copy? It's basically plagiarism, right? So I'll try to minimize the chances for you to do that. Now on the final, I mean, if our goal is to beat the final and beat the test and not really learn the information, you can do that on the final because they give you the calculator, let you use the calculator. Okay, but there's maybe only one question on the final that's of graphing these things. Okay, I don't want to graph this one, but I want to come up with the information. What's the amplitude? 2. Any reflections? No. X-axis reflection. Period. 2 pi over 1/2, which becomes 4 pi. So what is that going to effectively do? It's going to pull that thing like a, what was it, negative? Okay, so the blue one here is, or whatever color that is, that one's sine. Okay, do you see that this one here has been pulled horizontally, stretched horizontally? Okay. So that's what when this number here, when that B value is between 0 and 1, it's going to be a horizontal stretch. When that B value is bigger than 1, it's going to be a compression. Okay. Because essentially what happens is we're dividing by a fraction, right? And that turns into multiplication. multiplication by reciprocal. Let's do this one. This one I really like because it incorporates a horizontal movement. Okay. One thing I need us to understand, I'm gonna write this in red above it. They could present this as 3 sine of 2x minus pi over 2. And that red equation is going to produce, it is identical to that black one. Okay, written different, right? But the points that they produce are the same. And it's because of that 2, which is essentially our b value, being either, in this case, multiplied through, or in this case, factored out, right? I prefer to look at it as a factored out version because here we can see, I think, better that is going to produce a horizontal movement to the right pi over 4 units, right? If I look at the red one, a lot of people say, oh, it's a horizontal movement to the right pi over 2. Well, that's not accurate, okay? If you're ever uncertain about what your horizontal movement is, if you solve your argument for 0, 2x minus pi over 2 equals 0. 2x equals pi over 2. Does x equal pi over 4? So I get a movement of pi over 4 units, but what I don't like about that is that now, because that was positive, I'm now actually moving to the right pi over 4 units, right? Does that make sense? Where here, we've kind of trained ourselves to look at that and say, we're going to go counter to that. So that's why it's negative there, but we move to the right still. Does that make sense? So several different ways you can view that. All right, so what's the 3 going to do? What's that tell me? Amplitude. Amplitude is 3. Do I have any reflections? Okay, so the 2 there is your b value, right? And your period is equal to 2 pi over b. Good. So 1 pi is your period. Now the phase shift is that thing right there. So it's the pi over 4. I'm going to put capital R so I can tell myself to the right. Is that doable? No vertical movements here, and we should have everything that we need. Okay. So I'm going to develop where my pi is. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8 marks out. There's pi. And we're doing sine, right? There's pi. Halfway would be pi over 2. And what's this one over here? 3 pi over 4, right? Okay. And then obviously that one's 0. So my parent function points for the sine on that interval between 0 and pi. Sine, remember, starts at 0, 0, finishes at a height of 0, right? Halfway in between, crosses the x-axis. And then, so at the beginning, the sine function is increasing. So those are my parent functions, or sorry, parent points for the parent function sine, essentially, of 2x. Does that make sense? Okay. Now, here's the thing. Before I go on, I think it's useful to pay attention to make sure that when I shift these to the left or to the right, that my x-axis is written in terms of that shift, because it's easier to do. Okay, it's easier to see. Okay, I'm going to count over maybe 1 block, or in this case, 2 blocks.
There will be a meeting for any football players interested in playing football next year. There will be a meeting in the auditorium during Wildcat time today. Again, anyone interested in playing football next year, there will be a meeting in the auditorium during Wildcat time today. Thank you.
Okay, so the stretches that we can do, here we got a stretch of 3, right? So move that one up, that one stays, this one goes down to -3. Sorry, my fault. That one stays. This one goes down to -3. That one stays, right? Now the pi over 4 phase shift, you're going to take each one of those points and move it to the right, correct? So I'm going to take, we'll do this in green. this point here, going to go over to the right, pi over 4, right? And the reason I like writing my x-axis in terms of my phase shift is now I went over to whatever that distance, right? For me, it's 2 blocks. So isn't each one of these going to go over 2 blocks? Now, when I'm done, I need to know what this point right here, this ordered pair would be. 5, 5, or 4, good. And now I can connect those. That's terrible. It is a good idea because isn't over here, I mean, this graph should exist to the left of the x or the y-axis, right? Okay. So when I shift, that's going to come over here. So that point that I'm going to get over here, so kind of these things are symmetric, right? So I should be able to go over 2 and down 3. It kind of looks like that, right? Now, if you were to ask me, I think, and I had to mess with my period a little bit, but envision what your cosine function looks like. Reflect your cosine function. Does it kind of look like that? So there will be kind of a game that we play later on that says, how can I rewrite that function so that instead of seeing the word sine, you see the word cosine? Okay? So that'll be something that we mess around with later. I'm going to open up the 6th period assignment, not do it Monday. The thing about Math Excel, or sorry, WebAssign, is they give you something like this, and then they give you 4 pictures to choose from, right? Try to avoid using your calculator to choose the right one. Force yourself to practice this process because I think that'll benefit you in the long run. Have a great weekend.